Last week we talked about repair and restoration of the damages. And in continuation of that, we talked about retrofitting. Basically, we talk about retrofitting to reduce the vulnerability of the buildings. The focus has been on seismic. Now, most of these things are good also for cyclones because it's the integrity of the whole building that matters when it comes to the lateral forces from cyclone or from earthquake. Right. So today, yesterday I talked about various measures, which are used to retrofit masonry walls and the roofs. Now I have a couple of case studies here. Now actually this particular presentation has 3 case studies, but I'm going to be talking only about 2. But the PDF file you will get will have all 3 case studies. So one of the schools we worked on, this was back in 2016, was in Uttarakhand, the mountains, a place called Gopeshwar. Actually, Gopeshwar was hit by an earthquake back in 1999, called Chamoli earthquake, and there was some amount of destruction. So the school was also slightly damaged. And here, because we were working on some other things, the collector was very keen that we retrofit the school. So, it was good that, somebody like collector requests you and they give you all this support. So it was an interesting building. It was a small building. Actually, this is one part of the building here, which has the pitch roof. This is what that building is. This building here is right behind, you can see. What you see, this is, this part is the veranda in the front, and then there is one big large room right here. So all these things were constructed at different times, and they have some very interesting problems. Apart from the seismic vulnerability, it had some other issues also, which essentially they were to do with water leakages. And when you retrofit, you take care of all the things that you can. All right. So this is the plan of the building. So actually, this part, this is the original part of the building. This is random rubble masonry mud mortar. All right, pretty large rooms. Then after that, this room was added. This part has the tin roof. This room was added later on. This also is random rubble masonry. And this basically 3 walls were added and a reinforced concrete slab was added on top. Then this particular structure was added, which is independent and has its own 4 walls. Right here there are 2 walls. One is of random rubble masonry of the first phase of the building, and then this is all brick masonry. Typical government approach that even though locally things are made of random rubble, but now people want to bring in brick masonry. And then finally, this last is the storeroom and toilets were added. So things were added in 5 phases, and there was bad coordination, so there were a variety of problems. All right. Now this is looking at the condition prior to our intervention. So this is the back of the building. So, there's very poor drainage and, the roof, all this wall was also moss covered in bad shape. And this is the big, this is the newer building of brick masonry with the slab, where walls had some cracks and of course also there's water leakage. That's again the old building, the corner is coming here, the same roof overhang is coming here. So this is the corner, then the new building starts right here. So part of the roof was missing here. Then in the old building, there's cracks, bearing cracks right at its beams, and basically grade 2 and grade 3 cracks. And the roof itself, there's some pins were bad, so there was water leakages from there. And interestingly, here, once again you can recognize this is the first phase of building. And this is the new room that is added. And then then this chaja was added here, then this room was added. So right from this slab, the water would leak through these cracks down below, and was causing problems. Same way, at the end of this tin roof, right against the new building where it abuts, there is also water leakage there, which causes also deterioration. And too much of humidity, you have this growth that comes up, right? And basically it stays on the wall when the walls remain humid for a long time. But ultimately it does lead to deterioration in the wall. Anyway, this is the plan, so it gives you a good idea. The first phase building with the tin roofs. So essentially, the old building had earthquake damage in terms of breakthrough and breakthrough cracks. This newer building also had some cracks. This is the ground plus one building made of brick masonry with reinforced concrete slab. This particular room here had a lot of leakages, the slab itself, and the wall in this corner was badly damaged, and the room was dingy. It was very dark and it was just abandoned because of water leakages and just was extremely dark. So, and then since this chaja was added in front, there was no this proper connection, proper overlaps were not there. So water was leaking right through this joint and also like through this joint. So all these little problems also generally you take care of when you are working on the building. And also in the back there was a drainage issue which was also causing, which probably was the reason why there was humidity in that wall and the moss rising up there. All right. So these are the sections. We'll go back here. Yeah. There is one section right here, section 1.1, section 2.2, right? Section 3.3, and there is one section across here. So, section 1.1, basically this is through the new building. So you have reinforced concrete floor in between, and also the reinforced concrete slab on the top. So, and it had, I believe there is a band there. There is also a band here. But the opening and casement was missing, the sill level band was missing. We go back to IS 13828. What are the requirements for this, for this particular seismic zone? And if something is missing, then you take care of it. Right? So, IS 13935 gives very clearly what is to be done, what kind of reinforcement is to be added. So, based on that, all the belts are designed and the vertical reinforcement encasement around the openings is designed. So this is in the new building, and you can see part of this is actually wall on the ground floor. The upper floor is built right on this common wall of random rubble masonry. This is where the old building is. Now this is the old building right here. So this had gable. The gable bands were not there. So you require gable belt, you require lintel belt, you require sill belt, and then you require also the vertical reinforcement in the corners, vertical reinforcement around the door opening, and also around the window opening. This is then further down through the new building. You can see this basically you can see the slab right here as part of the cross section through the last room which had reinforced concrete slab on random rubble masonry, and also we are looking at the passage outside. So it's like this particular junction was a problem. This junction right here was also a problem. That's where the water was leaking. Alright, so this gives you a sort of picture of what measures were required in terms of the belts and the encasement, vertical and horizontal. These are some of the details. Now, this is again, going by IS 13935. The belt, IS 13935 basically recommends gauge 10 weld mesh. But gauge 10 weld mesh is extremely stiff, very difficult to handle. So we have been using gauge 13. Gauge 10, see when the gauge, you talk about gauge, when you say 10 gauge, which means 1/10 of an inch. Alright? So it's like what? It's 2.5 millimeters. So 13 gauge is a little bit thinner and it's easier to handle. So actually 10 gauge, if you don't handle it properly, it can hurt you. It can just there's a lot of ripping coming out of that. So basically, you decide how much of reinforcement you have as against 10 gauge, and additional reinforcement is added in terms of these this reinforcing bars here. And right here in this wall, it shows how this is the belt. This is the cross section of the belt, and this is the shear connector. So a dumbbell shaped hole is made, and an L-shaped shear connector, 8 mm deformed bar is embedded in it, just like the stitching element that we talked about yesterday. But stitching element will have a rod with two hooks at both ends, whereas this one is L-shaped, so that you have the leg here to which the weld mesh here is attached. All right. This is the vertical bar belt. So this is right here is the alignment of the belt in the corners. Okay, it shows the length, the width of it. So right here is the detail of the reinforcement on this in the belt, both of them, the vertical as well as the horizontal. Okay, and also on the right side you see here there is a vertical belt, and wherever there is reinforced concrete slab, you need the reinforcing bars overlapping, proper connector. You expose the reinforcement in the slab and provide proper overlapping connections. And on the left here, you see a typical detail of splicing or stitching of a crack. So you have a splice or a stitch right across, a ferrocement splice, which is 175 millimeter across, 14 gauge weld mesh, and this is right here and here. These are the shear connector. Once again, you have to make the through hole inside the L-shaped connector like we did for the belt. So you need one on either. This is the crack right here, so you need one on either side. And also, if the crack is long, then you need one every meter. So like the crack is this shape, so this center line to center line is 1 meter. In addition to that, the crack is grouted. You see these black dots. So those are the holes, the nipples which are put in, and the grouting is carried out. All right. So these are, some of the cracks. You see the cracks were exposed, and then the PVC nipples were put in place, and then the grouting was done in all the nipples. Here are the belts, the gable belt, the lintel belt, and once the grouting is finished, then the nipples are cut and the cracks are sealed. So, to begin with, all the cracks were taken care of. Then, in the last room that I talked about, which was very dingy and with leaky slab, so part of that wall had collapsed. So, that wall was rebuilt properly. And in addition, a window was added. So that utility of the room was increased a great deal with light and ventilation. The next thing is the vertical reinforcement, which is at the junction of the walls to ensure integrity between them. And also, they are properly connected with the horizontal belts. Now, actually, like in a situation like this, you have a crack right here. But this particular belt also acts like a splice across the crack. And same thing here. So you don't need any additional splices in situation like this. Also, when you have a situation like this, this often happens in buildings when you have a ventilator. Typically, that is just at lintel or slightly above the lintel, right in the middle of the alignment of the belt. So either you can bring it down or you can take it up, depending on what which will work, where you are able to accommodate the belt. And this situation requires special reinforcement within that, because when you have longitudinal stresses, tensile stresses, it is going to cause shear within this vertical part. So there is a special shear reinforcement that is added. Alright, so I'll not go into detail of that, but it's just good to know that it is also possible to change, to modify the alignment to small extents when you have this kind of opening. So generally, before you start installing the belt, you have to really go around, look at the building, and decide exactly which is the best alignment, which will have least amount of obstruction. Because in existing building, that is always the case, and there may be a situation where you may have to close one of the openings also. You may not have an option. Alright, then came the opening and casement. Now typically here, right here, you have a lintel, so you don't need encasement right here. So it's only vertical and is connected into the lintel. And oftentimes, you drill a hole and you just grout it, with epoxy or something. You just mix RL dye, get some sand, mix it with that, and just put it. And so we have used that quite extensively in the mountains because that's easily available in a hardware store. So even in random rubble also we use nails, but more often, the nail will go in 3 inches and then it'll hit a stone and then bounce back. So it's all trial and error, but having 2 shear connectors which are properly anchored in the wall. So same kind of shear connector you use for the vertical, or even for the encasement, because ultimately you are putting the ferrocement belts. So whether it is horizontal or vertical, the process is same. Right? There are no shortcuts in that. Alright, then here actually, this is the old building, phase 1, and then this is the phase 2 room, the slab. So there's gable sticking up. So, we have to put the gable belt right here on the outside. Of course, it's on both the faces. All the belts are on both the faces. So here again, this is where you can see these are the shear connectors right here, and that's the part of the shear connector. You can see the legs sticking out, and the hole is then filled up with concrete and is cured. And then the weld mesh is tied with the binding wires properly with the shear connector sticking out. Alright. And apart from all this, because this random rubble throughout all the walls, the stitching elements were installed. Like I said yesterday, 1 in every 0.8 square meter. So that pattern is also drawn on the wall. It's marked out, and it's approximate. So it doesn't have to be precisely. It all depends again, where the doors, windows, etc. are. So based on that, you will adjust. All right, let's move further. Yeah. So this is, apart from that, we had these beams on the top which had to be anchored to the wall. So we had MS flats which were connected with the belt. Now also there was a very interesting situation where we had one doorway. See, because all the doorways and windows were encased, but this particular doorway in the passage, there was no way we could put any kind of encasement. So here actually we made a very heavy steel frame and we attached it, because to make sure that if it moves, if it falls, at least the doorway remains open, and the teacher or the headmaster's office. So headmaster is able to at least get out of that place. And this is, we just had to improvise something. There was nothing we could do. Alright. Now non-structure. Yeah. So this is the original room, and this is the new structure. So this particular interface there was a lot of leakage, and there was absolutely nothing done. So the water would come down this wall and it will come in. So what is done here? There is something called flashing. So flashing is not a common concept in India, but in the US this is a very common concept and it works very effectively. So this is the wall, this is the other wall and the roof. The problem was right here, the water coming down into the leak. So here actually the plaster is removed, and then tin sheet is nailed in here, and there is some kind of sealant which is applied in the back, so the water will not enter, and the thin sheet went out like that. It's just a very simple arrangement, but it's called flashing. So this was done to eliminate the leakage from that.
So eventually the water goes to the roof only, like.
Yeah, once the water goes on the roof, then it will drain down, right? I mean, right here you see that the water is coming down here, and this tin sheet is nailed here properly with sealant, so the water will come out on this, come out of the roof, and it will drain down, right? So water falls down, otherwise, the water continues. Now, modern architecture is all straight. The architecture has come from the Western country where it doesn't rain, European country where it doesn't rain, so they don't have chajas and, in fact, what I've shared with you today, that Instagram thing, it has 9 wonderful visuals from the old tradition, and one of the things it says chajas, because in the modern architecture it doesn't have chajas, right, Mukul? So, alright, anyway. So this is one of the things, non-structural measures we undertook. Then the leakage is here. Alright, see, this was an interesting situation where we had this slab, right? That's the old building. This is the new slab which was put in later on. And then came this. This particular room slab is lower than here. But what they had done, they had just put a lot of concrete here, thinking that this would prevent the water from leaking in. But typically a crack developed here and water started going down below. So actually all this concrete was removed, and this was all smoothened, and then we placed the same sheet metal here. So sheet metal was also, again, there is also a different level difference here. So same way sheet metal was placed here and here. This is one of the options one should know when one gets into the construction, that flashing should be used. Alright. And then on the room which was leaking badly, we did waterproofing and renovated the room, and they got one new room along with the retrofitted school. So the principal was very happy. Alright, so this is the completed retrofitted building, all different rooms, the passages, and yeah, this gives you a little better idea of what was done on the top. See here, actually, from the tin roof on this passage slab, there was no problem of leakage because there was adequate overhang over that. Okay, the tin came out almost 9 inches, so there was no problem, and the water basically drained down from the slab. But here, between this slab and this slab, there is a gap of about 4 inches. So this is where we had to provide the tin. Then this room slab was even lower. So from this side as well as this side, we had to put the flashing. Okay, and then here the water, so the water does not fall right over the entrance. We had to put a little parapet and then get the water out. So this is basic to make it functional so that it doesn't cause inconvenience to people. And so that's a 2-story building done. And hopefully, if the education department picks up these ideas, they can go a long ways. Right? Now the situation here was that head of the education department of the district, he was very positive. So a couple of schools were retrofitted, they wanted us to do. Then came a new head, he wasn't interested, so the process stopped. So unless there are some definite, the state disaster management agency has some definite stipulations about what needs to be done. Because otherwise these kind of buildings, they will wait till they have some funds, then they will demolish them and they will build something. But then just think that by demolishing and rebuilding, you will be spending 5 times the cost of retrofitting. So for that same amount, you will be able to retrofit 5 schools. And that means you are spreading the safety net over 5 times the, more children. Okay. I mean, ideally, you need to get local contractors and train them. All right. And the next case is that. All right. So here we just went, local masons came and we trained them and they did it. I and Rupal were there for a month, our engineer was there for a month, and the project was carried out. All right. So, but once it becomes institutionalized, then there'll be contractors also will be able to, certified contractors and so on. All right, this was back in 2007 after the 2005 earthquake in Kashmir, Kupwara. Kupwara is a town, big town, and it was the subdivisional hospital, a big hospital. Before and after it was retrofitted. All right, now background, location, foothills of Himalayas, seismic zone 4, past major earthquakes, so many of them, 2005, 1885, 1863, and so on and so forth. But basically the frequency is pretty high, so 25, 30 years. This was October 8, 2005 earthquake in Western Kashmir. Basically, the epicenter was in Pakistan, in POK. But then, of course, there was a lot of destruction, a lot of fatalities on the other side. All right. So, a lot of basically the masonry houses were damaged. But also in Pakistan side, the schools were very, very badly damaged. A lot of schools were destroyed. Actually, on our side, it was a holiday in the schools. So, the fatalities were much less. On that side, the schools were functioning, so many more children died. Then the most common building types, type A, we talked about it yesterday, uncoarse reinforced masonry, random masonry, buildings in mud mortar. These are the most common types, and type C is unreinforced brick masonry buildings, which are typically the infrastructure buildings, like hospitals and schools many. Vulnerability, type A, it would suffer very heavy damage due to total collapse, and type C with many substantial heavy damage and some with very heavy damage. And that was the scene. Then in 2005, the need of the hour was the vulnerability reduction of type A buildings as well as type C buildings. It was multi-phase basically to demonstrate vulnerability reduction through retrofitting of public buildings. Build confidence of establishment in the people. This is very, very important. We can create trained people, engineers, contractors, and artisans. So we had this subdivisional hospital. All right. So year 2006, we undertook the disaster risk reduction program in Kashmir, and basically it was through public awareness and mason training program. And in the same year, we retrofitted a school near LOC, and also we retrofitted this particular hospital. All right. So the hospital is a 2-story building, and it's a T-shaped building, but there are 2 wings connected by a bridge. So there is no problem of asymmetry there. And see, load bearing 225 mm brick walls in lime mortar, good workmanship, and it had RC bands at the lintel level. But that's about it. It did not have any vertical reinforcement, nor did it have sill bands, nor did it have gable level things. And the roof and the walls were not connected. Intermediate floor was reinforced concrete slab. So the roof had a timber wall plate. That was a good thing. That's an important element. So basically, timber wall plate is a timber element that runs on the top of the roof, a good sized timber element, and the roof sits on it. So there is proper bearing on it. Okay. Alright, this gives a large number of rooms. There was almost 40 rooms per there, and 1400 square meter hospital. Those damage was essentially grade 2 damage. Or there were basically G2 and G3 cracks, but not too many. This is the plan, the rear wing and the front wing. The small ridge of timber in between. The roof plan just gives you an idea, 4-sided roof. Alright, let's see. So here, actually, this is the detail of this here. So you can see the wall plate. So all the trusses sit on this wall plate. Alright, and then with some connection in it, it was difficult to make out. Here is this particular section, XX is this. So you can see the corrugated tin sheets and the part of the truss, the top chord and the bottom chord of the truss, right here, this section. These are the ceiling joists, door joists, and the planks attached at the bottom. So there is, it's really not a false ceiling, it's a good timber ceiling. Alright. Now, there's inadequately reinforced brick masonry, absence of basic earthquake resisting features, seismic bands at multiple levels. Basically, they're bands at lintel level, opening and casement was missing, and the vertical reinforcement was missing. Quality of wall-to-wall masonry connection is questionable, because this is always, you see one wall being built at a time, and they do have leave the two things and they connect. So we would assume that that connection is bad. And excessively large windows, extra high walls in the rear wing. Yeah. Alright. Wall plate at even level but not anchored to the walls. Alright. So it was just wall plate was merely placed with bricks on both sides. Alright. The plus point, that reinforced concrete slab, it was a plus point because it provides diaphragm action. Also the CDI roof also provides good amount of diaphragm action on the top. Roof was resting on even wall plate, which I said earlier. And the false ceiling or the attic floor was also pretty strong. It was done with good timber, good connections. There was no falling hazards like chimneys especially. So likely damage in MSK intensity 8 earthquake could be grade 3 or grade 4. And being a lifeline building, it should retrofit to bring it to type D to minimize damage and prevent service disruption. Because minimizing service disruption is very, very important in disaster. Because the hospital should continue to take care of the hurt. Alright, just the fold outs of various wards. So wards are like on each floor, wing is the ward. So all this basically gives you an idea of the damage. But basically you have the whole picture of damage, the state of the building. Alright. So the retrofitting measures, basically seismic belt. We already talked about the specifications earlier, saying that now the vertical reinforcement here, we at those days, instead of using the weld mesh, we were using single rods. That's the earlier time. Then later on we moved over to weld mesh. So here the single rods were used, which are again connected with shear connectors to both the walls. And the wall openings, the openings are encased. And in the roof, in the roof base, the diaphragm was created by installation of struts and bracings, so that the proper, just like a reinforced concrete slab floor, similarly at the upper level also you have proper diaphragm to transfer the load to the shear walls. And also the roof was anchored to the attic floor. Alright, the trusses were anchored with steel brackets. Right? So this is just schematically shows all the measures which are to be done. Alright. So it shows the belts and it shows the tie rods, and what else it's showing. This, the lintel level belt, if it's missing somewhere, an even level belt. Alright. Ground floor and the first floor, and it shows the encasement of the openings, right, and the vertical reinforcement. Alright, so just schematically, but it's important to make this drawing so that everything is accounted for and that everything is carried out as per plan. So this in the roof, this is what I mentioned, that we have to install all these bracings with proper connections in the attic floor actually. And then of course the trusses were also anchored with brackets to the walls, and also actually the trusses were anchored to this wall plates with MS flats. So this is now before retrofitting. Alright, some of these damages. the piers between the windows it cracked in many places. But again, the damage level was not very high. So this is the installation of the belts, encasement of opening here, and so here, for example, see right here there is a little bend. So the encasement would just go up to the top and stop right there and be connected to it. You don't need anything at that level. Yeah, that's part of the attic floor diaphragm bracing and struts. Also entering the roof truss with the U-clamp right there to the wall. Also we had, wherever the vertical reinforcement was installed in the corners, the reinforcement would come up through the attic floor and would anchor onto this this wall plate on the top of the wall. Just an additional measure because it's there. So any measure to improve the integrity between all these different elements of the structure. Yeah, those are the brackets which were installed under every truss. Vertical. Yeah, this actually, I mean, here you see the shear connectors which are installed in the wall, and then comes a rod which is connected to that. You can see the rod here. And then just basically put plank out in the front and do concreting behind. And you do it every 3 feet so that there is proper encasement of the vertical reinforcement. Yeah, see this is the grinding of the joints with a cutter so that you have proper, for the proper, preparing the surface for proper connection. Some more visuals. Alright. Now, the difficulties. I mean, we are doing it in a very special place. The biggest thing, we see this we were to do with using a contractor. Alright. And it was required that we get what is called a Class A contractor. We had to get the contractor to build and execute an unknown technology. Alright. There were no contractors who knew retrofitting. So it was a big task to identify contractors who were willing to do it in first place. It took us 1 month to select and finalize a contractor. Procurement of material in J&K was very difficult from out of state because all these weld machines had to come from Delhi, and there were dealers with special permit for importing. They were not ready for loads smaller than a truck. I mean, we wasted few weeks, and not a really anxious weeks. We were wondering whether we'll be able to take the project forward or not. Government departments were of no help in that. We just had to go and talk to people and find somebody who is willing. Militancy. Kupwana is a hotbed of militants. Okay, so it borders with Pakistan, and so there were frequent agitations and public protests and curfew. Now it was a very interesting situation here in Kupwana. With horrible timing of time, you just don't get anxious. Yes, here we have this project going on in Kupwana. In the another valley, we 5 were sitting and working on the retrofitting training and retrofitting a school. And our main engineer from here is in Srinagar. There is a junior engineer at the site who had never ever gotten out of Ahmedabad. And the first time he is in a place like Kupwana. And then we hear that there is a curfew in Kupwana because there was some religious issue. So in the middle of the night, I call up the collector. The collector was nice enough to answer. And I tell him that, hey, please look after this fellow. He has never ever left Ahmedabad. And, he was really scared. So, but collector, of course, was very cooperative. And finally, things cooled down. Our engineer our engineer was very senior who was in Srinagar. But again, with this curfew, he could not even come there. So it was very, very tricky situation. But it was managed. So, yeah, frequent close down local markets, stoppage of work, adverse impact on our field staff, labor availability. Mid-July, they are busy in rice farming, so getting laborers. Now, okay, the best thing, the most interesting was working in the functioning hospital. All right. So this, being a hospital covering a very large area, the hospital was busy until 2 in the afternoon with outpatient, just jam-packed. So until 2 in the afternoon, we would work only on the outside. All right, we could not work inside. So after 2 p.m., we switched to inside. All right, and it was very interesting. We were given wards. All right, so they would vacate all the beds. But when our guys come to work, they will find even the beds which are vacated are occupied by some new patients. So it was a very, very tricky situation. Lessons in distant location, especially with difficult access, extra time should be kept for the material procurement. Chronically disturbed areas, extra time provision must be kept to account for the time lost and disturbances. Working inside a hospital, even schools also. We have worked in schools. Fortunately, in Delhi, we worked on 5 schools. There was a vacation time, 2 months. So we had no problem. But otherwise, it's a problem. I mean, especially children. You don't want anyone to get hurt with all this stuff lying around. All right. So it was a very close coordination with the hospital and management. And I mean, it was just so amicably done, and we had a great experience. Very, very nicely done. So the outcome is effectively demonstrated the efficiency, economy, and speed of retrofitting vis-a-vis demolition reconstruction. I mean, I mentioned yesterday that like if this hospital were to be rebuilt, it would take them a couple of years to get the funds, and then demolish and it'll be like a course of maybe 3 or 4 or 5 years. And during that time, people who are just flocking in the hospital every day, where will they go? I mean, will there be some sheds in which the hospital will work? So retrofitting is the best way to go in most situations. A demonstration of retrofitting option in a seismically active region where large number of existing buildings are vulnerable. I mean, if you do a few buildings, it can build up confidence, awareness among several engineers. Here again, we had a very funny situation. The collector had explicitly instructed the Bldg people that all their engineers must come and spend time. Hardly anyone came. Because they felt that if they come and learn about it, then there will be more responsibility put on their head. All right. First time tendering to appoint a Class A state registered contractor. I think this was a very important for the sustainability of the IIT. Execution of close coordination with the hospital management. So that went very well. And even for this, we had to get clearance from the health director sitting in Srinagar. And just at the last minute, we found this out. Professor Arya called me up and he said, you better do that, before going there. So we were in Srinagar, we went and met him. He was very friendly, there was no problem. But had we gone to Kupwana, then we would have to come back again and waste 2 days. So, yeah. And of course, I mean, like Operation Theatre, we were not able to work inside because it was being used around the clock. So everything had to be done from outside. So we had to put some, extra measures on the outside. Like I said, better, if we can do at least better, don't worry about the best. I mean, ideally, Operation Theatre should have been, retrofitted from inside also, but if nothing else, at least do it from outside. So that's it of the case studies. Like I said, the presentation has 3 case studies, but 2 is taken all the time. But your PDF file will have the 3rd case study. Those pages are hidden. All right. Thank you.